So we're going to be kind of going back and forth between me going over a few things and then you doing stuff throughout class today. So if we start with what we didn't get to last time of Lewis dot. If I did the Lewis dot for calcium chloride, which formula for calcium chloride CaCl2, recall that this is an ionic compound. So in an ionic compound, they don't create bonds, they give or take electrons. A quick reminder of just Lewis dot in general. Calcium is an alkaline earth metal. It's in the second column of the periodic table. It has 2 outer electrons. Now on that packet I gave you, some textbooks give a method of how to do your 8 dots. Left, right, top, bottom, left, right, top. We don't care about that. Know how many dots go around it. All right? For example, chlorine is a halogen. It has 7 electrons. Now typically I'll just go around in a circle, although I'm going to change my circle a little bit here for a reason. I'll show you that in a minute. So even though I drew my 2 chlorines slightly different, they both have 7 electrons around it, it's fine. One of the reasons why I do typically suggest doing one at a time, going around and then doubling up, is when you see a lone electron, for example, calcium has 1 lone electron here, it needs to pair up. If you have 4 pairs, that gets you to the octet, you're more stable that way. So sometimes this could be, well, how many times would chlorine bond if it was in a covalent compound? It would bond once. How many electrons would it accept if it was in an ionic compound? It'd accept 1. So by knowing the number of lone electrons, you can get that feel. But what happens is calcium, being a metal with a low ionization energy, chlorine being a nonmetal with a high electronegativity, there's going to be a transfer of electrons from the calcium to the chlorine. Doesn't matter that it's a 1-to-1 ratio. Again, it doesn't have to work out perfect like some of us thought with the MgO. It's more about those trends and attraction. So then my final answer, there's a few different ways you can draw the Lewis dot for an ionic compound, which by the way, it's not particularly a common thing to do a lot of Lewis dot with ionic. Again, we're going to do more Lewis dot with covalent, because then it gets into other applications that we're going to go over later in the week and next week. However, my calcium did lose 2 electrons, so now it's at a +2. My chlorine, although now we call it chloride, is a -1. Sometimes people put brackets around their ions. Quite frankly, as long as I can tell the difference between your minus sign and a dot, you should be okay. And then you can either write in a second chloride as well with a -1 charge, or some people will just draw 1 chloride and put a big 2 in front of it, a big 2 coefficient to show there's 2 of these. Then Lewis dot for ionic compounds does not show the structure very well. We'll talk a little bit about structure of ionic compounds and notes later today. We emphasized in Chem 1 to emphasize the octet rule. How do things get to the octet? It can't be by calcium covalently bonding, because calcium would not be at the octet. So metals lose, non-metals gain in an ionic sense. Maybe we have to know this when it comes to drawing dissolving, because that is something that we have to go over again. I believe that's going to be in the next unit on intermolecular forces. But overall, again, hopefully this is a quick reminder of what we did in Chem 1, of how to figure out the number of valence electrons and then what they would do. This is for ionic. Ammonia is not a compound that maybe you know the formula of just by looking at it, because it doesn't follow our naming rules. However, ammonia is a compound that is very common starting second semester with acids and bases. So when I was coming up with what 3 examples should I give, I thought, why not give you one that you will see later on in the year. Ammonia is NH3. At first I was going to do an acid and try to remind you of acid naming. Notice that ammonia, NH3, has the hydrogens on the back end instead of in the front, to try to show that it's not an acid, because if we put the hydrogens in front, now you should be thinking it's an acid. This is actually a base. Nitrogen doesn't fall into a particular family of the periodic table, but it ends in 2s2, 2p3. So there's your 5 valence electrons. Again, I would go around in a circle for those, because now you can see there are 3 lone electrons. Nitrogen and anything in that column would bond 3 times. That's where people that would instead draw nitrogen like that don't get that same advantage because it's already paired up. What's going to happen is hydrogen has 1 valence electron. I'm just going to put 3 hydrogens around it. Remember, hydrogen has an electron each. Well, now we can play connect the dots. Because when they're both nonmetals, they covalently bond. Remember, that covalent bond stands for 2 electrons. Remember, what that covalent bond actually is an overlapping of orbitals. So the 1s orbital of hydrogen overlaps with the 2p orbital of nitrogen. That's going to lead us into something later on next week called hybrid orbitals. This is sp3 hybridized. You'll have to know what that is starting next week. Covalent compounds has a lot more Lewis dot with it, because we can start talking about the shape of molecules, the bond angles, the hybridization, how many sigma and pi bonds there are. So there are things to add on to that. That's why covalence definitely more useful than ionic when it comes to Lewis dot. And again, this example will be used, and we'll show how it's a weak acid second semester. I'm sorry, a weak base second semester. Okay? The hydrogen technically is not an octet, it's a duet, because the first shell is filled with 1s2, so it's still stable that way as well. I want to do one more. This one is a combination of the two. Sodium hydroxide, sodium's Na, hydroxide's a polyatomic ion. I think one of the things I'm going to do is send you today on the Remind app. Well, Josie, let's just call it a music video that I made. Last year, I don't know what came over me in early December, but I decided to make a video showing how to do the mechanism of a Lewis dot for a metal and a polyatomic ion to the song Louie Louie. So I call it Louie Louie dot instead. It's one of the finest works I think I've ever had in my teaching career. Plus, you don't have to listen to my voice when you watch the recording, which is nice, because I don't know if you guys have ever watched any of these afterwards if you're gone, but sometimes I've watched them to, did actually record, and then to hear my own voice, it's just sodium, 1 valence electron. Oxygen has 6. Again, instead of pairing up the last 2 individuals, I kept them solo to remind you with 2 lone electrons, it needs to pair up those 2 electrons. Hydrogen has 1. If you were asked to do the Lewis dot for an ionic compound with a polyatomic ion, you have to do both types of bonding in this. You have to realize that at some point, sodium, being a metal with low ionization energy, it will give an electron. You also need to realize, however, that oxygen and hydrogen are both nonmetals, so they will covalently bond. I typically start with the polyatomic ion, and I make covalent bonds. Because then what I do at the end is I look and see where am I short of an electron or 2. That's where the metal will come in and save the day. So to start off with, the O and the H are going to create a covalent bond. Now, again, if I'm trying to keep score of what's happening here, my hydrogen is already stable now. It paired up its lone electron, it's stable. Oxygen, however, is at 2, 4, 6, 7. It's 1 electron shy. And that's where sodium would give to get that to the octet. And if I were to draw that out then as my final answer, sodium has a +1 charge because it lost an electron. Hydroxide, and I'm going to make it a little bit neater now, has a -1 charge because it gained an electron. A little bit more common to put a polyatomic ion in a bracket, I think. I've seen questions that just ask you to draw the Lewis dot for a polyatomic ion. So draw the Lewis dot for CO3 minus 2. Once you have that negative charge there, that means that this should have one more electron than it normally does, because it gained an electron. Now the good news is that typically you are not going to have to try to figure out the most difficult Lewis dots there are. But at the same time, these three models that I've just shown you, ionic, covalent, and a combination of the two, we all need to be comfortable with. Because to some extent you will be assessed on it. Some years it's a little bit easier than others. Some years they give you the elements in order, and you just have to draw the bonds in to make it work right, and the extra electrons. Some years it's just a blank thing, and you have to draw the entire thing in. But either way, there's a lot of applications to Lewis dot, and that's why we have to go over that. And in particular, the covalence, where you're going to see more of that. A little bit about structure of solids. But then I need to get into what's referred to as lattice energy, which deals with these ionic compounds and how they're held together. So, first off, let's just talk about solids in general. Again, remember, gases, Delaney already came and left. Gases very spread out. So spread out, you can't see them. That's that invisible form of matter. Liquids are loosely held together, but there's a flow about them. And liquids can take the shape of their container, whatever that container may be. Solids are in a much more rigid structure. I like to think of the states of matter as how we work within this school. For example, you're kind of in a rigid structure right now. You're in the solid formation. Solid particles are still vibrating, just like you're moving about, but they're in a fixed spot. When I say go ahead and start working, we move about. There's more of a flow about what we do, but we're all still contained within here. And then when that 940 bell hits and you just scatter all throughout, we're more like a gas. Now, if you notice these three diagrams, one of the things that you do not need to know are these different types of solid structure specifically. So, the specific names of them you don't have to be aware of. I like to bring them up just to show you, and I'm going to show that to you with the styrofoam balls here in a minute, just how tightly packed things are. I was grading a Chem 1 lab report, and there's a lab where we give them carbon, but it's not really carbon, and they have to talk about why it's not. And one student, although this answer really wasn't great for the question I was asking, said, well, it can't be pure carbon because it's not either diamond or graphite. And those are the only two pure forms of carbon, which first off, that's not true. But they might not know about Buckminster fullerene. I understand that. Not everyone knows about carbon in a 60 chain ring altogether. But same element, it must be stacked a different way to give it slightly different properties. So when I show things like a simple cubic, that would just be the atoms stacked directly on top of each other, more or less, over and over again. Now, if it's face-centered, what happens is, instead of being on top of each other, they find kind of a groove to sit in. And then it's back to the first one again. So they're a little more tightly packed in that sense. And then when I look at body-centered, boy, that one's even a harder one to do. It involves layer 2 being in the grooves of layer 1, layer 3 being in the grooves of layer 2, but it's not the same grooves as layer 1. But then layer 4 is back to being the same as layer 1. So there's different ways that things can be stacked together, and that can give things like its density of stuff. Again, thinking back to the Chem 1 lab I just graded, again, a lot of solids are more dense than liquids, but mercury is a very dense liquid, and like barium is not a very dense solid. Depends on how they're all stacked together. Now that stacking goes for any type of solid, so I'd like to start off by just kind of talking about how solids are arranged. But then we need to move specifically into ionic, and that's really the goal that we have here. Now again, on the bottom right-hand corner, you don't have to write that down because you have that goal sheet already. Move this though. And since this won't let me move it anyways, I'm not going to show you what it all says. But recall that an ionic compound is not a molecule. When we give the formula of an ionic compound, we are indicating that is the simplest repeating unit within that solid stacking structure. So to isolate one sodium and one chloride for sodium chloride, it's really unheard of. Sodium chloride is just that repeating unit over and over again. But if you think back to the styrofoam balls, you have to have oppositely charged particles next to each other. Because if it's the same charged particle next to each other, it's going to repel, it's going to break apart. So when you take salt in your hand and you kind of rub it between your fingers, what you're doing is shifting this. And you're shifting in a way that's all going to fall apart. For example, we have a nice arrangement here, but if all of a sudden I shifted the desk one over and we have Tyler next to Grant, all hell is going to break loose. Because those two don't get along. They're too similar with each other. They repel. They're going to break the whole classroom apart. But if we have Tyler next to Davina, now we're okay. So again, with the ionic compound, their solid structure, not only do you think about that stacking, but it's got to be the opposite charged particles that are next to each other. So we represent the formula, but we have to realize it's just that over and over and over again. NaCl's, NaCl's, front, back, top, bottom, forward, backward. Okay? So, what we need to go over that's hopefully a little more new than today is how to tell one ionic compound from another. If all ionic compounds are basically repeating units of oppositely charged particles, what makes them a little bit different from one another? And that's what's referred to as lattice energy. Again, that connection between structure and energy is, I think, a fairly good theme today. We're going to talk about structure versus energy with ionic compounds right now, and then give you a little practice with it. And then you're going to see that at the end of the hour with covalent compounds. How long is a bond? How short is a bond? Lattice energy, as it says for the first bullet point, is the energy needed to separate these ions. Because if right now Tyler and Davina are the glue that's holding them together right now, well, how do we rip them apart? Again, think about ionization energy in those photoelectron spectrographs. How much energy is it to pull things away that are naturally held together? Second bullet point, very common for the different type of solid to be asked a question relating to how it melts. Because recall, like I started this little lecture with, solids are held together in a rigid structure, liquids have a flow about them. When I say go ahead and work, Tyler and Davina and Grant can go wherever they want. So it's not like they're forced to be in one specific spot. So when you melt it, you loosen up those attractions. You mentioned as well that dissolving things is dealing with this lattice energy, and we'll talk more about dissolving next unit when we talk about intermolecular forces. But that leads me to my last point on this slide, is that the energy holding an ionic compound is based upon the charge between the particles and the distance between the particles. So charge product I'll explain with an example here in a bit. But then ionic radius, again, the distance between two ions, again, there's a reason why we just got through with the trends of the periodic table. Even when we did Lewis dot, I tried to emphasize electronegativity and ionization energy. Because now, as we start really getting rolling into class, and I don't even think we're really quite there yet, I'd say by the end of first semester, now we are in the middle of AP Chemistry. Making connections between what we did and what we're doing is a must in this class. Because what you will eventually see on test questions on a Part A, Part B, Part C is grabbing topics from all over the place. And if you can recognize how these things come together and relate to one another, that is a really good sign for you. And that's something I've emphasized year after year, regardless of the new workup of AP Chem this year. So, I could give you 3 ionic compounds: beryllium oxide, lithium oxide, and silver oxide. And I could ask you to arrange them in order of increasing melting point. So in other words, what would melt first, what would melt last? Question. This would be something new for us. my first suggestion would be to figure out the formulas for each of these. Beryllium's a +2, oxygen's a -2. I'm even going to write the charges down. So it's just BeO. Lithium's a +1, oxygen's a -2. So it's Li2O. And you can do your cross and drop if you want to, or however you balance charges. Silver oxide. And silver is a transition metal, so that one's a little bit harder possibly for you to know the charge of it. Silver's a +1. And I don't know if you noticed, but the little brown dropper bottles for the Chem 1 lab, that's the silver nitrate that you worked with over and over again in Chem 1. Nitrate's a -1 polyatomic ion, so if you know that, if it's AgNO3, then it has to be a +1. And oxygen's a -2, which means the formula is Ag2O. I kept the charges for a reason. That reason is there are two determining factors on the melting point of a solid. The first, and what I think is the more important of the two, is what's called charge product. If this were a math class, and I said product, what would you do with the two numbers? You'd multiply them, wouldn't you? 2 times 2 is 4. I don't care about the positive versus negative. 2 times 1 is 2. 2 times 1 is 2. In other words, beryllium and oxygen have a higher amount of attraction towards each other. Meg Stimson, going to homecoming in a couple of weeks?
Yes.
That's going to be a magical time, Maggie.
Ja,
Oh, man.
Ik vind het daar. Ik vind het concert.
Oh, she's ditching you for music,
Yeah.
huh?
Gewoon bij staan.
Every year, assistant principals send out this email asking if we would like to chaperone for homecoming. And I don't know if there'd be anything worse for me ever in my life than watching high schoolers for 4 hours all up in each other's business. That's kind of what happens at a dance, right? I haven't been to a dance in over 20 years, so I wouldn't know for sure, but I'm just thinking that's what happens. And I'm guessing one of the roles of the chaperones is to make sure things don't get a little too, you know. I'm recording this and then I have to post it, so we have to keep this kind of PG at the time, probably unlike with the homecoming dances, I can only imagine. If you have two individuals that are only a little bit attracted to each other and they're dancing, they're probably going to dance normal. Fair statement? So as a chaperone, I don't have to put in much work to separate them if I have to. However, if you have two individuals that are hugely attracted towards each other, they are going to be locked in. And that's when possibly the chaperone has to, you know, separate. And it might not be easy, because when you have two individuals that are, you know, really attracted to each other, it's hard to tear them apart. That's what charge product is. A +2 and a -2 has a greater amount of attraction than a +1 and a -2. Sorry, I forgot my minus sign here. That's why beryllium oxide would have the highest melting point. It's got the most attraction. If melting means to get them out of their fixed position and pull them apart a little bit, to loosen that attraction, the more attraction, the harder it is to pull them apart. That narrows down now to lithium oxide and silver oxide as what is the easiest to pull apart. They have the same amount of attraction. However, and this goes right back to the trends of the periodic table again, silver is further down on the periodic table than lithium is. And as we know from the trends, as you go further down the periodic table, you gain another shell of electrons. In other words, silver, being bigger, is further away from oxygen. And if silver is further away, even with the same amount of traction, two things that are further away from each other are easier to pull apart. Again, when I show you the gold thing and it talks about Coulombic attraction, or Coulomb's law, all it's talking about is things with opposite charges are attracted to each other. And the closer they are, the more attraction that can exist. Although, as you'll see with covalent compounds, if things get too close, there could be repulsion as well. So again, silver oxide has a melting point of 280 degrees Celsius, which means that's how much energy is needed to make it go from a solid to a liquid, to overcome attraction. Lithium oxide definitely kicks it up a notch because lithium is smaller than silver, the ions can be closer together. Lithium oxide is a little over 1400 degrees Celsius for its melting point in order to loosen it up. Beryllium oxide, not only is beryllium small, but there's a higher charge, there's greater attraction. So beryllium oxide is over 2500 degrees Celsius for its melting point. So what I would like us to do is you picked up a sheet on the way in that goes over this a little bit more. Now sometimes we could even give you the ionic radius. So on that sheet it gives you the ionic radius in PM, which is picometers. So sometimes you don't even have to know the trends of the periodic table. Just look at the distance between ions to help figure it out. However, if I give you 10 minutes right now to practice that, then we can come back over again and start talking about metals and alloys a little bit, and then that gives us time to still do the covalent part. All right, so again, showed you styrofoam balls, structure of solids. We just did a little bit of the ionic, but then let's talk a little bit more about metallic bonding. Remember what a metal is the cations and valence electrons that are just floating around. Because that is just cations and negative electrons, if we relate that back to what you just did, metals also have really high melting points. Because, again, it's just oppositely charged particles that are held together. It takes a lot to rip those apart. But I wanted to remind you of how that metallic bonding works. And this picture is showing those negative electrons in between the nuclei. Because besides graphs, diagrams are a big thing. I mean, I mentioned drawing dissolving before, but there's some years where you don't draw the loose dot for dissolving. You have to draw like a representation of water. Now, a representation for an ion. I was mentioning to Josie that after next class, I'm going to have another AP classroom assignment up. And they will show you diagrams at times. And that's what I like about their things versus WebAssign. Is their questions a little bit more authentic to what you'll see. The problem is it's just not as user-friendly yet as WebAssign, where it can show you whether you got it right or wrong right away and stuff like that. So again, metallic bonding, really we covered in Chem 1. We will talk about it here and there sporadically throughout this first semester, but it's more of just an understanding of what does it mean to be a metallic bond, different than the ionic bond, which is metal losing to non-metal, covalent bond, sharing of electrons because of the orbitals overlapping. This is just, hey, we're all attracted to the stuff in the middle, and that's what's holding it all together. Last thing to mention then, an alloy is a metal with at least one other element. Two vocabulary terms that was on your goal sheet for alloys today is substitutional alloy and interstitial alloy. And I gotta be honest with you, this is the first year that I am actually going over this, because I never knew we had to go over this. All of a sudden last year we were looking at a practice test and these two terms came up. I'm like, uh-oh. So, okay, let's go over what these are really quick. You can see on that picture in front of you, and again, I apologize that yours is in black and white, although it looks like there's a slightly different color for the substitutional one. The pure metals on the left-hand side, just arranged in a certain pattern. Substitutional, notice how it's not only red, but then there's blue circles in there. Take out one, put another one in the same spot. Again, just think of the root word, not to get all Englishy on you here, but to substitute is to trade things out. If I were to have a substitute teacher, they would just come in and take over, and they'd do everything exactly like I'm doing, so we wouldn't miss a beat. Any substitute teacher would teach AP Chem with a breeze. Interstitial alloy, on the other hand, is going to be on the lower left here, where you can see we're filling in those cracks. Remember the styrofoam balls before when I showed you that sometimes they can not just line up on top of each other, they can get in a little bit more. You could fit more in there, in essence. And I have the desks arranged more in a substitutional pattern, but that gives us room to roam in between. What if we just started putting people in the middle? We could do that. We could fit them in there. That's what interstitial is. Putting inside that metal already. As I mentioned on the top then, brass is an example of substitutional. I mean, your zinc and copper are similar size if you look at the periodic table. So when you put zinc and copper together as an alloy, they fit in that regular pattern. Interstitial, though, an example would be steel, iron, and carbon. Carbon higher up on the periodic table, smaller size than iron. So it fits in the cracks. Let's have a classroom of high schoolers, but then let's also invite a classroom of kindergartners in here. Well, where do we put them? Well, they can just sit on the floor in between. That way we can watch them a little bit too. They would fit in just fine. Especially in the AP class, they fit in just fine. And then you can see in the bottom right-hand corner, I typically don't see examples of the two combined. But, you know, different alloys made could make that happen. One of the reasons why steel is such a strong alloy is because when you fill in those cracks, now it's held together a little more tightly. You can't have movement of those layers. So unlike the other things that we went over today, there's not a lot of practice we can do with this. This is more of, I've seen examples of this before. Again, last year I saw it in a practice test. So I need us to be aware of it. And I'm not a huge fan of memorization of vocabulary, but we should know these two alloys. We should know in general what a metallic bonding looks like. What does it mean to be metallic bonding? Free electrons floating in between the positive cations. But then an alloy is taking that metal and adding something to it. Maybe another metal, could be a non-metal. And then how does it fit in there? That's what substitutional and interstitial are trying to demonstrate. Okay?